So to better develop our idea of how sets work, how they interact, how we can picture the connections between different objects in groups of sets, we're going to turn to an invention of John Venn that was credited to him by Lewis Carroll in 1896 that you're probably already a fair bit familiar with. Or look at Venn diagrams, where Venn diagrams are just, as you've seen them before, bubbles, where you might have some overlap, you might not have some overlap, you just have these different things you can have to talk about how groups of things come together, split apart, where they might share things and where they may not share things. It's a diagram that you should have familiar with. Unlike a lot of what we talked about here with set theory, I imagine everyone in this class has seen at least one Venn diagram in their life. Actually, anyone who's watched my videos has, because I put them in the last couple of sections for precisely this reason. They're really good for representing set problems. So I'm not going to get in here and talk about a definition of what a Venn diagram is, except to say that for us, usually when we talk about a universal set, we put that in a box, and then we talk about our sets in them, we put them into bubbles. But you know a little bit about what a Venn diagram is already, hopefully. There's not a whole lot in here I can give for a definition. Really, the best thing to do is to just take a look at them and see what we mean when we talk about them in this way, instead of the more loose way that you might be used to. So for the example we have here, we are given the Venn diagram, and what we want to do is determine what the universal set U, as well as the sets in it, A and B, are in terms of their elements. So we've got this diagram here that we have to work with, and as we can see, we have that box there with the U inside of it that says U consists of all the things in the box.
What's in the box?
And then if we want to determine our pieces, what we have for A and B, we just have to look at what those bubbles are and what's inside of the bubble. Like I said, you should be somewhat familiar with how a Venn diagram works at this point. It's just we're being a bit more exacting here. And for this, we can see that bigger bubble A, putting it into roster notation because we don't have a whole lot of things in here and they don't follow a particularly nice pattern I can recognize, would consist of the objects 1, 2, 5, and 6, just as numbers here. They might have some special meaning in a different context, but for us, that's what we're looking at. That's the set A. Then similarly, the set B would just consist of the things 3 and 9. And then we also have those extras out there that aren't in either circle, but are contained in the box. So when we want to talk about the set U, that does have a bit more of a pattern, but just to keep with the way I have been working, I'm going to write this all out here in terms of a roster. We have 1, 2, 3, 4, 5, 6, 7, 8, and 9. Or if we want to think about this in terms of the natural numbers like we did in the last section, we could say that this is the set of natural numbers up to 9. So just pay attention there, and we're looking at the elements inside of a set for a Venn diagram. We basically want to see what's in each of the bubbles, and then what's in the whole box, where if it's in a bubble, in a box, it's in the box. Generally, we don't treat these things as being sort of like holes that you pull out and remove pieces from. They're contained in there. And when we call the thing U the box, we're not going to go outside of it very often, because the entire point is that for our problem, U, as it were, is the entire universe. It's the universal set, after all. And then hopefully we can start to see a bit of how these sorts of patterns we're familiar with might represent in different Venn diagrams. That we have here the case where our two bubbles don't overlap, but we can also have ones where they are completely overlapping, in which case you have something like two equal sets, or one is completely contained within another, in which case you have something that's a bit more of a subset relationship, or you have something where there is a small amount of overlap between the two of them, which is probably what you're the most used to, and also, in a lot of ways, what we're most interested in here. So, with a bit more of an idea of what we're talking about, let's get one more example, specifically in that last kind of arrangement with an amount of overlap, but not complete overlap. So for this, we're given the Venn diagram and want to be able to determine the sets A and B as collections of objects, as well as in terms of those numerals. So with this, we have both the labels on the bubbles, as well as the Roman numerals in the bubbles, and the objects in the bubbles as well. So there's a lot going on here, but just don't worry too much. Basically, those Roman numerals are just extra representations. So we can see that that I, or 1, is inside of the A bubble. That means that 1 is part of A, along with 2, that extra part out there that's in the overlap. And in particular, if we want to define all of the elements of A, again, I'll use roster notation here. When you've got that few things, really, unless you're intentionally being weird about it, you just use roster notation because, well, there's only 4 of them. A, B, C, and D. Making sure I did copy my diagram correctly, but that looks like it's the right collection. And then for basically the same reasons, B is that other bubble over there where we have the numerals 2 and 3, along with the elements there that B is going to be. D, the overlapping element, along with E, the element all on its own, where there's also that group 4 that's not technically in either of those bubbles. That's where you get the sort of pulling out sort of idea that talks about the other things in the universal set U that are not in A or B. That would be F and G, and that is actually a good place to bridge off the gap to start talking about our operations. Because, well, we've got a universal set of things, but that doesn't mean that the sets inside the universal set have to include all the things in the universal set. F and G aren't in either, so what might we want to call those? And that is the type of idea we're going to be looking at with things like unions, intersections, and complements in our operations.